In this short video, we're going to look at stem plots. We're also going to look at possible shapes of a data distribution. Those shapes are symmetric, bell-shaped or normal, skewed to the right, skewed to the left, and uniform. This is an example of a stem plot. In a stem plot, we have a section we call the stems and a section we call the leaves. And a stem plot organizes quantitative data by grouping together values, usually by their tens places. It is good for small to medium-sized data sets, but not for extremely large ones. This is what I mean by tens places. If I have the number 64, 6 is in the tens place, 4 is in the ones place. So for most stem plots, you'll see the stems represent the tens place and the leaves represent the ones place. This specific stem plot represents this data set, these numbers shown. And these numbers represent the percentages of three-point shots made by Michael Jordan during his 13 years with the Bulls. So if you look at this specific value, it represents 28. In this situation, that means 28%, which means that specific year, 28% of Jordan's shots were three-point shots. And if you look at this specific value, it represents 35. So when reading these numbers, you have to look at the stem and the leaf. So this 35 means that specific year, 35% of Jordan's shots were three-point shots. This is another example of a stem plot, and sometimes you'll see a 0 in the stems section. That means there's a 0 in the tens place. Sometimes you won't see any leaves at all within one of the rows. That means that there's no data values that start with that number. So in this case, there's no data values that have a 2 in the tens place. If I look at this specific data value, that represents the number 6. And if I look at this specific data value, that represents the number 35. Let's look at one more example of stem plots. Sometimes you'll see stem plots with a key at the bottom. This means that you have to read it in a different way, that you're not going to read it based on tens and ones place. This key is telling me that all of these data values represent decimals. And it's showing me that the stem would be the digit located before the decimal, and the leaf is the digit located after the decimal. So this value in the stem plot represents 0.5, and this value in the stem plot represents 4.0. I also want to point out that usually stem plots are organized from lowest to highest value, and that's what we see here. Notice the first values that show up are 0.5, 0.7, 1.1, 1.3, 1.5, and it continues in increasing order. Let's now talk about describing shape. And the reason we describe the shape of a distribution of data is to help us identify overall patterns. The first type of shape is symmetric, and this is any distribution where the two halves are roughly mirror images of each other. This is one example, and this is another example. Notice these distributions are symmetrical. A real-life example that would probably create a symmetric distribution is the heights of all Americans. If you think about it, women tend to be shorter. Their average height tends to be lower than men. So this data distribution would create two clusters of data. The first cluster would have a high frequency representing the common height for women. So there would be a cluster there among the lower values, and then there would be another cluster among the higher values representing a common height for men. Another shape is called bell-shaped or normal. This is a special kind of symmetric distribution that has one peak and two sloping tails. These are two examples. The first example is a stem plot. It's a little hard to see the bell shape unless you tilt your head to the side. The second example is a histogram, and it's much easier to see the bell-shaped, which we see drawn in black over the histogram's bars. An example that would probably create a bell-shaped distribution is IQ scores, because when measuring IQ, most people are going to be average, so you're going to see the highest frequency in the middle, and then you'll see people who are below average, and that will continue to decrease in frequency on the left side. You'll also see people who are above average, and that will continue to decrease in frequency on the right side, creating that bell shape. And this is actually called bell shape because the shape of the distribution looks like an old-fashioned bell. The next two shapes we're going to talk about involve the word skew. So it's important to understand what it means to skew. To skew means to suddenly change in direction or position. For example, if you're driving a car and you make a turn too quickly, your car might suddenly skew off the road because you changed your direction too quickly. One shape is called skew to the right. This has one peak and a long right tail. This occurs because most of the data is concentrated among the lower values. This is a histogram that is skewed to the right. Notice there's a cluster of data among the lower values. This is where most of the data is occurring, and we only have a few data values on the right-hand side where the higher numbers are. This is a stem plot that's skewed to the right, and to see the shape, you just might have to tilt your head to the side. A real-life example that would probably create a data distribution skewed to the right is the number of children per family. Because if you think about it, most families don't have a lot of children. They might have 1, 2, or 3 children. So you won't see a lot of data values that are larger. You won't see a lot of data values that say 7, 8, or 9. Skewed to the left is the opposite. It has one peak and a long left tail. This occurs because most of the data is concentrated among the higher values. This is an example of a histogram that is skewed to the left. This is another example. This is a dot plot that is skewed to the left. And notice in both of these examples, there's a cluster of data on the right-hand side where the larger numbers are, and there isn't that many data values on the left-hand side where the smaller numbers are. A real-life example that would create this distribution is age of teenagers who can drive, because typically the teenagers who can drive are in their late teens. They might be 17, 18, or 19, but you won't typically find people who are in their lower teens that can drive. You won't typically find a 13 or 14-year-old who is able to drive. The last shape is uniform. It's approximately a flat line since there's minimal difference in the frequencies at each level. This is a histogram that is approximately uniform, and this is a stem plot that is approximately uniform. You notice that the frequencies in each category are approximately the same height. The example that would create this distribution is tossing a fair die, because if you toss a die a specific amount of times, the frequency of getting a 3 would be just as high as the frequency of getting a 5 or a 6 or a 2, etc. Based on what we know, let's look at this example. Assume we're looking at the visitor time in minutes that patients at a hospital receive. What shape would you predict for the data distribution and why. So you have to think about what the numbers would potentially look like when collecting different visitor times. Would they be really small numbers? Would they be really large numbers? Would it be a balance of both? The data distribution would probably be skewed to the right because we would probably have a lot of small numbers, but not a lot of large numbers. Most people might make a brief visit, maybe 30 to 60 minutes, so most of the values in the data set will be among the lower values. So you won't see larger numbers like 120 minutes, 150 minutes, 200 minutes, etc. And if you need a reminder, this is what skew to the right looks like.